Let's go over the material to cover question number 1 and question number 2 in the lecture worksheet. So we're going to go into get an equation and as well as a relationship, which we're going to call the right-hand rule, to connect the velocity of a charged particle with the applied magnetic field and the exerted force on the charged particle that the magnetic field creates. So we have a charged particle that is in motion. So remember that if a charged particle is not in motion, meaning that it's stationary, you're not going to exert a force on that charge. So as a charged particle is in motion through a magnetic field, there is a magnetic force that will act on this particle or that's going to be exerted on this particle. The force is at a maximum when the charge moves perpendicular to the magnetic field. Okay, and the force on the moving charge will be directed perpendicular to this magnetic field. These two properties will come from the orthogonality and they will give us the direction using the right-hand rule. So now I'm going to write the equation that's going to relate the force exerted on a moving charge. So here we're going to have that the force is given by Q, the charge of the um, moving charge. So it can be, in this case, we're going to keep in mind that it's going to be positive charge. Okay, so we can think like a proton. Then we have Q V B sine theta. So in here, the V is the velocity of the moving charge, and then B is the external magnetic field. External magnetic field. Okay. Now, if I rearrange this equation for the magnetic field, meaning that I want to solve for the magnetic field giving the exerted force, then I can rearrange this equation and we'll have the magnetic field to be equal to F divided by QVB sine theta. Let me put a box here. Now, a very good question you might have is, okay, what is this theta here? Okay. And theta is the angle between my variables of V and B. So theta is the angle between the direction of motion and the applied magnetic field. Okay, so the next couple of questions, we're going to have different directions of motion for a proton and then the applied magnetic field. And this is why you have a maximum at theta equal to 90, because when theta is equal to 90, that's when you have a angle which gives us the perpendicular component. Okay. All right, so really quickly, I'm gonna go over a few units for the magnetic field. Let me put it here. So the magnetic field will have a unit that is a Tesla, denoted by the uppercase T, and a Tesla is equal to a Weber per meter squared. A Weber per meter squared is also equal to a Newton per Coulomb times meter per second. Now we've used this unit before because a Coulomb per second is what we call a ampere. So this is also equal to Newtons per amp meter. And a Newton per amp meter is also another unit, which is a Gauss. Here I'm going to write Gauss. So 1 Tesla will be equal to 10 to the 4 Gauss. Okay, so these are the different types of units that you can have with magnetism. All right. Now, in a laboratory setup, we can normally reach magnetic strengths of 2.5 Teslas, and in a superconducting magnet, we can actually reach 30 Tesla strength. Now, these values can actually be exceeded with special equipment, but for now, let's assume that most of the information that we'll have will be between 0 and 3-4 Tesla. And then if we go higher than 3 or 4 Teslas, then we're going to assume that we are using special equipment. The equation for, or that relates the magnetic field, the applied magnetic field, the exerted forces, the velocity, and then the, doesn't go here, the charge will be given by the right-hand rule. Now, what is the right-hand rule? The right-hand rule is actually a rule that comes from the cross product, but for our case, we can just simply memorize. And if you follow a set of directions, you will get the correct direction of force, velocity, and applied field. So the right-hand rule states the following. So when you have a problem, you're going to extend your hand and you're going to point the fingers of your right hand. Okay, don't use your left hand because it will not work. You're going to point the finger, expand the fingers of your right hand in the direction of velocity. Okay. Then, once you have your hand stretched and you're going to point in the direction of velocity, curl your fingers 90 degrees and you're going to curl your fingers in the direction of the magnetic field. Okay, so you're going to have to orientate your hand such that the direction matches the direction of the magnetic field. And when you do that, you're going to keep your thumb pointing in the direction that it's naturally pointing. And then your thumb is going to give you or show you the direction of the force exerted on the moving charge due to the essence of this applied magnetic field. So here I did a drawing of a hand, a beautiful hand, and I'm going to point the direction of motion to follow the direction of the fingers if they were exerted or if they were just stretched. So this is your V. And this will be a vector sign, meaning that the direction has to be taken into consideration. Now, when you curl your fingers 90 degrees, you're going to have an applied magnetic field at 90 degrees from this velocity. So this will be 90 degrees. And then your thumb shows the direction of the applied, of the exerted force, excuse me. Okay. So here we have if a charged particle is going, as you see in the screen, to your left, and then there's a magnetic field out of the screen, then there is an exerted force pointing up, which is the force that the charged particle will feel due to the presence of the magnetic field. Now, if you have a negative charge, what do? Very simple, you're going to get the exact opposite direction. So in this case, if I would have had a negative charge, then my force would go down for negative charge. Okay. All right. Let me go over question number 1 and number 2 with this information. I'm going to scroll up for a second, and I just want to make sure that we are on the same page. Here we are solving for the force, and the force is given by QVB sine theta, where theta is the angle between the moving charge, the velocity moving charge, and your applied magnetic field. And when I rearrange this equation for B, I have B is equal to F divided by QV sine theta. This B here, I made a little mistake while I was copying. So there's only one B. So B is equal to F divided by QV sine theta. Again, the angle B and V. Okay. All right, so let's do question number 1 and question number 2 in this lecture worksheet 5. So question number 1 is a question that is quite simple because we're going to plug in the values that we have into the equation, but we have to practice this right-hand rule to get the correct directions. So we have a proton that moves with a speed of 1.00 times 10 to the 5 meters per second through Earth's magnetic field, which has a value of 55 microtesla. So I wrote that information in the first two lines where we have the velocity and the applied magnetic field, which is Earth magnetic fields in this case. So when the proton moves eastward, the magnetic force acting on it is directed straight upward. And when it moves northward, there is no magnetic force that acts on it. Okay, so really quickly, I made two arrows where I am illustrating the information that I have. On the left side, we have the velocity that goes eastward, and on the right hand side, we have the velocity that goes northward. So let me scroll down a little bit. There is no magnetic force acting on a proton when it is going north. Okay, I can write northward to be a little bit more correct. So when I have a velocity goes northward, there is no magnetic force. So in this case, I have the magnetic field that if the magnetic field is going north in the same direction of the velocity, then there is no force. And likewise, if the velocity is going eastward and then my force is coming upwards, so in this case, upwards is going out of your screen. Let me draw a force that's coming out of the screen. Then that will give me, by default, a magnetic field that is also pointing north. Okay. Again, this is information that we're giving. Okay. It's simply to practice the right-hand rule. So this will be the magnetic field. That's a B. All right. So the first part is, what is the direction of the magnetic field? Well, we deduce that by using our right-hand rule, but let me write this a little bit more formal. So we're traveling eastward. Okay, so this is the velocity. The force is going upwards, okay, force, and the magnetic field will be north. Okay, so if you try and use your right hand, extend your right hand towards the right of the screen, where we can assume that the right of the screen can be east, and here we have a north. And then you're going to curl your fingers 90 degrees from east to north. So you're going to curl your fingers from the direction of velocity to the direction of the magnetic field, and then your thumb is going to point out of the screen, which is what we call upward. Okay. That is the only arrangement where those two pieces of information will match. So if you want to take a little break, pause this video and try to use your right hand such that those two pieces of information match what we have in this three parts. Okay, traveling east, force upwards or out of the screen, and the magnetic field going northward. So part B is calculating this. So we're going to calculate the force exerted on the charge, so no problem. And then in this charge, we're gonna have a proton. Okay, so we're gonna keep Q as being positive. So I'll write the equation here. So I have F is equal to Q VB sine theta. So now plug in the values. So my charge of a proton will be 1.6 times 10 to the negative 19 coulombs, multiplied by the velocity, which is 1.00 times 10 to the 5 meters per second, multiplied by 55 microtesla. Again, this micro is 10 to the negative 6. And I'm going to squeeze in sine of 90 here. Okay, sine of 90 because the angle between V and B is 90 degrees, which is what we call the maximum force, because the maximum will occur when you have sine of 90, which gives you 1. Okay. All right, so when I plug this into your calculators, you will get 8.80 times 10 to the negative 19 newtons upward. Okay, so direction and the magnitude. Okay, part C is a comparative question. It says, okay, calculate the gravitational force on the proton and compare it with the magnetic force. So we did this type of problem a couple times in previous worksheets for us to compare the gravitational force with, in this case, the force that will be exerted on this proton due to the presence of the magnetic field. And I'm going to write F sub G for gravity will be mg, F vector, G will be a vector. So the force of gravity is the mass of the proton. So we have a 1.67 times 10 to negative 27 kilogram. We're going to multiply by 9.080 meters per second squared. And we have 1.64 times 10 to negative 26. We have kilograms, meters per second squared, and we call that a Newton. Okay. All right, so what will be the force, the electric force, if there were a electric field, and I'm going to write the value of the electric field before I plug in all the numbers. So the value of the electric field is 1. Was that a 5? Excuse me, this is a 5, my bad. 1.5 times 10 to the 2 newtons per coulomb. Let me change the color. So we have the force due to electric field, and there we have an equation that will relate the force, charge, and the electric field, which is F is equal to QE. So we have 1.60 times 10 to the negative 19 coulomb multiplied by 1.50 times 10 to the 2 newtons per coulomb. Okay, and you will have 2.40 times 10 to the negative 17 newtons. This is 17 newtons. So in this part C, we're comparing the gravitational force with the electric force once again. And then we have 10 to a negative 26 compared to 10 to a negative 17 newtons on this proton. All right, so that question was mostly getting acquainted with this equation and understanding a little bit this right-hand rule. Question number 2 is quite similar, so let's go straight to it. Question number 2 tells us that we have a proton that is moving at 8.00 times 10 to the 6 meters per second along the x-axis. It enters a region where there is a magnetic field of 2.50 Tesla, 60 degrees of the xy plane, okay, from the x-axis. I'm going to draw this so that it can be a little bit easier to visualize. The first part is find the initial magnitude and direction of the magnetic force on the proton, and then we're going to calculate the proton's initial acceleration using Newton's equation. So let me first draw with the information that we have. So here I drew a X, Y, Z axis, and we have the XY plane given by this green square that starts off the x-axis and goes to the y-axis. So as the proton enters this region, we have an applied magnetic field of 60 degrees from the x-axis on this xy plane. Okay, this will be the plane. And the charge is moving on the x-axis. So I'm going to do an arrow that will point towards this x-axis. Now, when I use the right-hand rule again, so on this right-hand rule, we're going to point our fingers in the direction of the velocity, namely the x-axis, and curl your fingers on the xy plane towards the vector B, the applied magnetic field. And in doing so, your thumb is pointing in the positive, my bad, your thumb will be pointing in the positive z-axis, which is our force. Okay, so here we have our three components for the right-hand rule: velocity, applied magnetic field, and exerted force. So let's plug in the values. So the force, just like we did before, is QVB sine theta. So for this one, we have 1.60 times 10 to the negative 19 coulombs multiplied by the velocity, which is 8.00 times 10 to 6 meters per second multiplied by 2.50 Tesla sine of 60 degrees. Okay, and we will get a value of 2.77 times 10 to negative 12 newtons. Now here I'm going to write positive z axis. All right, let me underline this result. Okay, and then the second part of this question is to find the acceleration. So we are going to use Newton's second law. Let me write this down. Newton's second law. Okay, so we have here that the acceleration will be equal to the force divided by the mass. So here we have the force, which is the value we just solved, 2.77 times 10 to negative 12 newtons, divided by 1.67 times 10 to the negative 27 kilograms. Okay. So here we have an acceleration to be 1.66 times 10 to the 15 meters per second squared. Okay. And there we have completed question 1 and 2. And again, the main purpose of these two questions is to use the equation for the F is equal to QVB sine theta, manipulate depending on the variables that we're given, but most importantly is to use this right-hand rule to understand the direction of the V, B, and F vectors. Okay, right, I'm going to pause or stop this video right here, and then I'll present the next part of the material, which will be question number 3 on a different video.